So in this lecture, we'll be learning about cost estimating techniques and risk appraisals. In your previous lecture, you learned about contract documents, the standard form of these construction contracts, the general layout, what clauses are, and what are claims. So this lecture will be covered in CLO number 3, which is to apply operational cost estimating technique and to organize risk appraisal for small projects using method related charges. In this lecture, we'll be changing from lawyers to accountants, and you'll be learning the difference between estimation and guessing. You'll also learn what costs are in construction. You'll learn how to calculate these different types of costs. And you'll learn how to identify, quantify, and mitigate risks. This is a jar of jelly beans. How many jelly beans are in the jar? We can either guess or we can estimate. So what's the difference between guessing and estimating? They're quite different. When you guess, you usually make a judgment without little evidence or without little knowledge. You can also be correct, but it might just be luck. But when you estimate, you use your knowledge and experience to value something. So it's based on expertise or familiarity. When we talk about estimating, people usually say a ballpark estimate. You have a ballpark and you need to find out or estimate where the ball will land in this ballpark. So how can we reduce the size of our ballpark to make more accurate estimates? Well, for one thing, we need a lot of information. But what information do we need? Let's look at estimating construction costs. Underestimating construction costs can lead to financial loss, where suddenly we find we don't have enough money to complete the project. Overestimating can lead to a loss of client, where nobody wants to take our project because it's too expensive. So there are two approaches to estimating construction costs. Usually, we can do the bottom-up approach or the top-down. Let's look at the bottom-up first. Using the bottom-up approach, we take our indirect costs and we add them to our direct costs to get our total cost. On top of the total cost, we'll add our desired profit and we reach our required price. In the top-down approach, we take a competitive price, subtract the profit that we are allowed to have, put in our indirect and direct costs, and we get our target cost. Now, there are different types of estimates. There are design estimates, which usually are made by the design team, architects and engineers. These are based off drawings. There are bid estimates. Usually these are given by the contractor to the owner. They are called bid estimates because when the contractor bids for a project or submits a proposal for a project, they usually have some estimates of their own. And lastly, there are control estimates. This is to monitor the project during construction to make sure that the budget is on track and does not go over the budget that was proposed in the bids or in the designs. Now let's move on. Do you have what it takes to become an estimator? These are the qualities of a good estimator, and generally they are qualities of a good anything, really. So If you have all these qualities, you can become an estimator. To prepare an estimate, you need drawings, specifications, and the rates at which different items of work are carried out. An example of a rate is how much does it cost to pour 1 cubic meter of concrete, for example. Now, to calculate an estimate, the steps involved are taking out quantities. So we extract the measurements from these drawings and we place them in a measurement sheet, or we also call it a dimension paper. Once we extract these measurements, we work out the volume and area or any other unit and have the value in recognizable units. This is usually in square meters or cubic meters, for example. And we abstract them, which means we take the volume and area and we multiply them with their prices. Now, there are different types of costs in a construction project. They're basically divided into direct costs, indirect costs, and also markup. Now, we'll be looking at direct costs first. Direct costs are comprised of labor costs. And labor costs, on the other hand, is comprised of direct labor costs, which is basic hourly rates. How much does a worker get paid for each hour? And this is the greatest uncertainty in project estimation, because sometimes when work isn't done, it needs to be extended, and that requires more manpower and more man hours to complete. Indirect labor costs are the additional costs to the basic hourly rates, such as tax and insurance, and they're usually about 25% to 50% of the direct labor costs. Now, material costs are all materials gone into the finished structure, which is quite simple and very direct to calculate. There's also equipment costs. Sometimes these costs can come from owning a vehicle, or maybe if the construction firm does not want to buy the vehicle, they can lease it or they can rent it. And how much do these equipment cost to operate? And lastly, there's the subcontractor price, which usually in a big construction project, the construction firms may subcontract or employ subcontractors to do other parts of the work. And when these subcontractors have finished their work, they'll give quotations to the main contractor to get their payment. So these must be reviewed extensively to make sure that the costs are fair and justified. Now, indirect costs usually consist of project overhead, or we can also call it job overhead. And these are costs not directly related to any construction work, but they are required for the construction work to proceed. They are around 5 to 15% of the total project cost. And examples of these are listed here, which you can read in your own free time. All right. Now, let's move on to markup. Markup is usually 5% to 20% of the job cost. Includes the following: general overhead, cost to support company construction program. The profit. So any company is a business, it's not a charity. Profit is used to make sure that the company grows and the company does not go bankrupt after one project. And also contingency. These are funds that the company can use if things go wrong. So any project, not only construction, should have some contingency funds. Also, you may notice some overlap between general overhead and job overhead. And this is completely normal. Some things may go into general overhead and some things may go into job overhead. This is an example of a cost estimate. Ignore all the different numbers. What I want you to look at is this column right here, direct cost. The total at the bottom here is the sum of all of these numbers at the top here. Now, we take our job overhead and add it to our total. And then we add our markup, which is 15% of this. And then we add our bond. Bond is usually a deposit, and it's not really covered under any particular category. And of course, you need your sales tax, and you get your project bid. This is a very simple example. Now, let's get your calculators ready, because we are going to be doing some calculations. So, what is a cost index? When we do calculations or estimations for construction costs, we need to make use of a lot of indexes, because indexes allow you to move costs between different time periods. They indicate change in cost over time. In other words, they account for inflation. Remember, when something used to cost 1 ringgit 10 years ago, now costs 10 ringgit, for example. They are usually accurate to within 20 to 30% of the actual costs. It's very time efficient and very effective to get a rough estimate of the cost of the thing that you're trying to estimate. They're valuable for preliminary planning, which means you just want to get a rough estimate. But what about its limitations? Well, we'll take a look at cost index and see what are the limitations of this. This is the formula we'll be using, CA over CB, where CA is the estimated cost at the present time. So usually the time that we want to find, which is right now. Cost at base time B is sometime in the past. And also we have IA over IB. So the index value right now. And also an index value in the past. Let's look at an example to see how these can be used in calculations. So the construction cost of a building in 1970 was 128,000 ringgit. How much would it be in 2021? Okay, so we have our formula here, but what are our variables? So CA, or in this case, I'll use C 2021 is, we don't know. That's what we're trying to find out. C 1970 was 128,000. The index, oh, I forgot. There it is. The index in 1970 was 28. I think we'll move these to a different page. Okay, let's go back. So, the cost in 1970 was 128,000. The cost in 2021 is unknown. We know that the index in 1970 is 28.7, and the index in 2021 was 242.7. So let's just plug all of these into our equation. Now remember, the ones on top is the one that we want to find out now. The one here at the bottom is the one in the past. So C 2021 over C 1970 equals 242.7 divided by 28.7. or C2021 is equal to 128,000 multiplied by 242.7 over 28.7. And calculating this with your calculator, you should get this number, which is 10,824,250 and 87 cents. So that's quite a jump from 128 about 31 years. Oh no, not 30, 51 years ago. So in 1970, if you had this amount of money, you were quite rich. Okay, that's it for cost indexes for the time being. Let's move on to cost estimating relationships. So a CER is a mathematical expression of cost as a function of one or more variables, like y equals to mx plus c. It's basically an equation. It's used to estimate plant and equipment costs. They are different from index relations because they estimate based on design variables such as weight, force, pressure, and speed. And there are two commonly used CERs. One is the cost capacity equation, and the other one is the cost capacity combined with cost index equation. We'll be taking a look at this one first. Cost estimating relationships, and the cost capacity equation is the first one we'll be looking at. It's also called the power law or the sizing model. It uses design variables to estimate costs. Now, what are these design variables? They can be horsepower. It can be, let's say, watts. Any other thing related to equipment. And we have these values of x, which are right up here. Oops, it goes spinning there. So if x is 1, nothing's really different. It's just the relationship is just linear. But if x is less than 1, then that means the economies of scale is in effect, which means that the product is manufactured at a very efficient rate. It's mass produced. So x will be less than 1. But if x is more than 1, then there is called diseconomies of scale, which means that this item is quite difficult to produce. It's not produced on a mass volume, and you're going to find that the calculation is going to make the price a bit more pricey. Now let's look at an example again. Here, a 100 horsepower air compressor costs 35,000 ringgit. Estimate the cost of a 300 horsepower compressor. The correlating exponent, or x, is 0.85. Let's do the example here. So C of 100 horsepower is 3,500. We don't know what C of 300 horsepower is, so we'll just put a question mark there. We don't know. X is 0.85. Now, what about Q's? So Q of the 100 horsepower is 100 horsepower, of course. Q of the 300 horsepower is 300. Now we'll just plug all this into our equation. Oh, and I forgot to mention Q is the capacity of equipment. It's the capacity of the equipment. It could be horsepower, it could be meters, cubic meters, or anything, because different equipment has different roles. So it depends on the equipment that you're trying to look at. In this case, it's horsepower. So that's the value of Q. Now let's put all of these into the equation. So C 100 horsepower over C 300 horsepower. Oh, remember again, A is the one that we want to find out. A is the one now, but in this case we don't have time, so this is the one that the one that we want to find out. So this will be let's say one we want to find. Okay, so this is not correct. Let me just, yeah, there we go. So C 300 horsepower divided by C 100 horsepower equals to 300 divided by 100 to the power of 0.85. So C 300 horsepower equals this value multiplied by 3,500, and you should get your answer as 8,904 and 74 cents. Okay, not as much a big of a gap than previously, but we don't have time to take into account. All this equation does is it just takes into account the different capacities. It doesn't take into account time. So what can we do? Let's attach our cost index to the end here. So we get the cost capacity combined with cost index equation. So we're combining what we've learned in the two previous equations. And this will take into account factor of time because of this right here. And these are all the that's the equation spinning, and these are all the variables in this equation. Now let's look at another example. It's the same example from previously, but we have more information now. So a 100 horsepower air compressor costs 3,500 in 2016. And we want to estimate the cost of a 300 horsepower compressor in 2021. X is 0.85. The cost index in 2016 is 143. And the cost index in 2021 is 272. Now let's write all of this down. So CA, but in this case, I'll just write the year. So C 2021, we don't know. C 2016, was it? Yes, C 2016 was 35,000. Not 35,000, sorry. Oh, not 35,000. 3,500. Q 2021 is 300. That's the one that we want to find. Oh, there we go. There's go again. Goes haywire a bit. Okay, let me just erase this. Alright, there we go. Okay. I'm not quite up to the level of Khan Academy yet, guys. So bear with me. So Q 2021 is the one that we find out. It's 300 horsepower. Q in 2016 is 100 horsepower. X is 0.85. Okay, now we're getting to the index part, which is I 2021 is 272. 272. I 2016 is, let's see, 143. Now let's plug all of this in. Actually, we don't need to plug again because we've already calculated for this part here. But let's just put it in just for clarity's sake. So C 2021, we don't know what that is. 2016 will be 3,500. Okay, and 300 over 100. Remember, the thing that we want to find is on top, so this one is also on top, to the power of 0.85 and multiplied by 272 divided by 143, and you will find that C 2021 will be 16,937 and 69. There we go. That's taking into account the factor of time there. All right, now the last piece of estimation here is the unit cost of estimation. So usually in a big project, construction project of a building, for example, you want to break it down into smaller parts and estimate the cost of each part so that you can sum it all up and get the total cost. So in this example, we have a preliminary estimate, which is the entire floor of the building. So that's really a rough estimate. So in this case, the estimate here would be how much does a floor cost? One floor. How much does one floor of this building cost? And the second part is a detailed estimate. So it's getting more narrow. The scope is getting narrower. It's getting more detailed. So now we're looking at how much does a single floor panel cost, not a single floor. And the last one will be the engineer's estimate, which is quite detailed. And this goes down to, for example, beams on the floor panel. How much does a single beam cost? And of course, there's the equation there again. It's very, very simple, very straightforward. You just get your number of units. How much does each unit cost? And just multiply them together and you get your total cost estimate. Right. We have an example, but it's already been calculated here. So cost to build a 250 meter square. And this is your unit N. And is 6,750 per meter squared. So this is your U cost per unit, and you just multiply them together and you'll get your CT cost, unit cost. Okay, now we're moving into risk appraisals. Now before that, I'd like to ask you a question. What's the difference between hazards and risks? You might hear them used interchangeably, but they're actually different things. A hazard is something that can potentially cause harm, like a shark swimming in the water. But a risk is when you are exposed to that hazard. So if you go swimming in the ocean where there's a shark, that's going to be a risk. But if you don't go swimming, then the shark is just a hazard. Another example would be if I had an electrical wire and it's plugged into the wall right here. Just imagine that's a plug there. Oh, there's a plug there. Okay, and there's maybe some exposed wire there. Then it's going to be an electrical wire there. Now, if this were in the middle of the road where people walk all the time, this would be a risk, a very high risk. It is also a hazard and it is also a risk. But if it were to be, for example, in the basement where nobody walks there, it would be a hazard, but the hazard would have a very low risk. Now we'll look at how these two, hazard and risk, interchange or interact with each other in the later slides. So here, anything that can cause harm is a hazard, but the risk is how great the chance that someone will be harmed by that hazard. Now, basic steps in risk management. Number one is you need to identify the risk. Once you identify the risk, you need to quantify the risk and put it into a number. Then once you get that done, you need to mitigate the risk or try to reduce that number. Now first, let's look at risk identification. So you need to continuously identify risks. Even once you've done the risk appraisal at the beginning of the project, you need to continue doing it as the project continues, because risks might constantly change. New risks might come. So you need to identify all risks. Trying to identify all risks is a waste of time, but we need to identify the most critical and frequent risks. So don't try to list all of them, because you definitely won't be able to list all of them. You just need to choose which is the most critical and frequent. It's a process of discovery. You need to brainstorm a lot. And the most frequently identified risks in the literature, according to these two, Siraj and Fayek, 2019, are these three: change in inflation rate, design errors, and poor engineering. Now you might be wondering, what does inflation rate have to do with the risk? It's not dangerous. It is a risk in the terms of the financial sense. So a project might cost 2 million today, and in the next 5 years it might cost 3 million. So that's also a risk, not a health or safety risk, a financial risk, but a risk nonetheless. Now we go to, before that, this is just a small excerpt from Siraj and Fayek, which you can find the name of the paper here. Take a look at it and see all of the risks that they identified in construction. It's a nice paper, actually, quite long to read, but just take a look at this table number 6 if you can. It's quite interesting to see all the risks that they have compiled. Now we've gone to risk quantification. Once you identify it, you need to put a number on the risk. Now, usually when you have a risk, you just need two numbers: the probability of the risk and the impact of the risk. Probability is how likely something is to happen, and impact is how badly it would impact the project. And you just multiply these two together, probability and impact, and you'll get your rating for the risk. This is an example. So let's look at adverse weather. The probability happening is 1, which is low, actually. Maybe they are living in a place where there's not a lot of bad weather, and if it does happen, if bad weather does happen, it would have minimal impact on the project. So multiplying these two, you get number 1. Now let's see this community protest. Maybe the construction project is very controversial, and the local people might not agree with the project. So the probability of this happening would be quite moderate. It's at number 2. We can consider number 2 as moderate, and the impact would be quite high, number 3. Maybe if they do protests, it might hinder the work a lot. So you multiply these two, you get a number 6, and that's quite high, actually. And what number to use, 1 or 2, that's basically up to you as the engineer to decide what number to use. Usually you can just assign it a number from 1 to 3. So it has 1, 2, and 3, with 1 being low and 3 being high. But it's totally up to you. You can go up to 4, you can go up to 5. It's all a matter of consistency. If you use this scale, then you need to use it for the whole risk appraisal. You can't keep changing things around. Now, once we've quantified the risks, if we put it into numbers, we need to try to reduce those numbers. And this is called risk mitigation. You can do this by either reducing their probability, you can reduce their impact, or you can do both. You can try to reduce both. So which ones to mitigate first? And usually you try to mitigate the ones with the highest certainty and highest impact. And certainty is just probability. So make a graph like this: certain here, unlikely here, low impact here, and high impact here. So this place will have high certainty and high impact. So do this first, then you can do these two, and then this one will be the one that you do last. Now you can prepare a risk mitigation plan and shows how you will address each risk. Like I said before, risks are not static, they change as the project proceeds. They must be periodically identified, not just at the project start. And this is a good an example of a table. So you have your types of risks here, the probability, the impact, you multiply them, you get your rating, and then you can write down the potential consequences if this risk really does occur. So what are the consequences here? Now you can write down your mitigation strategy. You can check your drawings, or for example, to avoid this risk, and that basically addresses this risk rating. And once the project proceeds, you can reevaluate, and maybe some of these may go down. The probability may go down if once you evaluate further on. Since you have done all of these mitigation strategies, your probabilities and impacts may go down. But for your assignment, remember you have to do a risk appraisal for your assignment. Stopping here at this part. Oh dear. Let me just erase that first. Point options. Erase all in outside. All right. So you can just do, basically you can just do this table right here, and that will be fine. Okay. You can just do it at the project start. Put the probabilities here. Put your impacts, risk rating, potential consequences, and mitigation strategy, and you should be done. That should be fine for the project. And remember to do for environmental, health, and safety aspects. So let's see, this is design risks, so this doesn't fall under any of the categories. So like we mentioned, environmental, health, and safety. This does here. Safety, of course, is safety. Be more specific, try to break it down a bit, since you're not covering all of the factors. But like I said before in the previous slide, let's just go back. Okay, these are the types of risks here. So you can see environmental is here, health and safety is here. So there are few risks right here that you can take a look at and see which one applies to your project. Then you can pick out these, which ones of here, and then you can try to determine what are the probabilities that they happen, and also their impact, and do the risk risk mitigation strategy that I mentioned at the last slide there. Okay, now yeah, we're basically done. This lecture is complete, so I hope you all can proceed now with your project, and looking forward to seeing your presentation. And remember, safety does not come with luck, it has to be prepared. All right, so stay safe,